In addition to taking a geometric series and manipulating it to turn it into a power series to fit our function, we can also just use some algebraic methods in order to come up with our power series. Here, take a look. We're going to start with two series. Our f of x is defined by this a sub n times x of n, the series defined on that one, and the b sub n x to the n is our g of x series. So initially, we're not going to use that. We're just going to focus here on this power series represented by f of x. I can make myself a new power series by just plugging something else in here for the x, some sort of constant being multiplied times that x, and this is what it looks like. F of k to the x there. And then you can see what it would do is I would just stick in a k in front of this x, and then I would give the n to both of those things, and then you can see that it's k to the n, x to the n. So here's an example of that playing out. So we just looked at f of x is equal to 1 over x, that's what we started with, and then here's the composition. Basically, I stick 2x in there, so that should be equal to 1 over 1 minus 2x. So really, this is the function maybe that we're trying to represent here, and then we want to kind of recognize it as, oh, it's just an offshoot of this one if I just stick 2x in there. Well, we've already come up with a series for this one, and as a matter of fact, this will be something that we write on our memory card because we want to have it memorized. It will come up on the AP exam. I almost guarantee it. Okay. Anyway, so doing this composition here, I'm going to stick a 2x in here, stick a 2x in here. That'll be 2x to the nth power, and you can give that nth power to both of them, and then it's 2 to the n and x to the n. I'm curious, whenever we do this composition like this, are we going to get the same interval of convergence? Here, let's take a look. So since we're treating this as geometric, all we have to do is take that common ratio here, which is 2x, force it to being positive, and say that that's less than 1. All right, so I can take the 2 out because it's positive already. So 2 absolute value of x is less than 1, and divide that 2 over absolute value of x is less than 1/2. So we can see that we've changed our radius of convergence. I do believe that first time it was 1, and now whenever we apply our absolute value rules to this, it's now sandwiched in between -1/2 and +1/2. Again, I don't have to check the endpoints in this case because we based it off of a geometric series. So now we didn't get the same interval. You won't know. You just got to check it and see. All right, so that first one is just doing some composition, plugging some constant value times your x inside of your function. That's pretty straightforward. Another thing that we can do is that we can, instead of just plugging in, say, 2 times x, how about x to the second power, x to any kind of power? It's a capital N here in this notation to distinguish it from the summation index that we are starting at 0 and increasing, right? It is just some power that we plug in there. And so now if we plug that into our power series here, this is x to the big N all raised to the little n, while power to a power means that you multiply those exponents, which is what happened here. So let's take a look again. Our good old-fashioned f of x is equal to 1 over 1. F of x is equal to 1 over 1 minus x. Again, we want to have that thing memorized. It keeps coming up. It keeps coming up again and again. Let's say I plugged in an x squared in there. So if I plugged in an x squared, it just goes in there where that x is. That's straightforward enough. And then building a power series from this. From this one, I just plug in our x squared in the place of x. That's going to be x squared to the nth power, which makes that x to the 2n power. So basically, we only get the even powers on our x as this new series. So that's what this would now be represented as a power series. So here, again, I'm curious to know, how does that affect our interval or radius of convergence? If it does at all, do I have an extra bedroom? No, I sure don't. Okay, no worries. I got it covered. So let's try this thing again. Our common ratio here is x squared. We want to force that into being positive, which it already is. It's less than 1. All right, so again, it's already positive, so I can get rid of that absolute value symbol. Absolute value inequality, you solve it by finding its critical values, and the critical values is where it's equal to 1. Critical values in this case is not the same thing as, it's where its derivative is 0, different critical values. Anyway, take the square root of that. X is obviously equal to plus or minus 1. You throw that thing on a number line, and let's see here. On this number line is 0. I got a negative 1. I got a positive 1, right? I get open circles around this guy, and then just do a test value here. If I plug in a 0, 0 squared pretty much is less than 0, so I get all the stuff that's in between here. And our interval of convergence is negative 1 is less than x, which is less than 1. Wow, we got the same exact interval of convergence that we had before. So the first time it changed, the second time it didn't change. How are you going to know? You're not. You're just going to have to try it out and see. All right, so let's look at example 3. Find a power series for f of x is equal to 1 over 1 plus x squared. Hey, look at this. Doesn't this look familiar, 1 over 1 plus x squared? Isn't that the derivative of a function that we know? Isn't that the derivative of arctangent or something? I wonder if that's significant. I wonder if that's the reason why we're doing this. Probably not. Anyway, so can I do this as a composition, as we did before? So I think I'm going to start it off by trying to manipulate it as the sum, go away, sum is equal to 1, no, not 1, a over 1 minus r, right, the geometric one. So we'll have to fix this guy right here. So it's going to be 1 over 1 minus a negative x squared, right? And then representing that as a power series, n equals 0 to infinity. Our first term is 1. I'm not going to write it down. Common ratio, negative x squared to the nth power. Power to a power, you're going to multiply those exponents. But again, think of this as a negative 1 that's in there that also gets that nth power. So I have negative 1 to the nth power. And then I also have x to the 2n power. Okay, all right. So radius of convergence, well, we sort of almost already did this on that last one, because it would be, did I say radius? I actually want the interval of convergence. All right, if you take the absolute value of that common ratio, force it to be less than 1, well, take away the negative sign because it's already absolute value is going to make it positive, and then it turns into what we just solved there. So we know that that is in between a negative 1 and a positive 1. All right, this is significant, right? Because the domain of this is all real numbers, but the domain of the power series, which represents this function, is only from negative 1 to positive 1. It diverges everywhere outside of that. All right, now, what we were looking at in this video, though, was could we have gotten this through some, composition? So first of all, this looks like it is a composition on the function f of x is equal to 1 over 1 plus x, where we are sticking in an x squared here. So 1 over 1 plus x squared. All right, so do we have a power series for that 1 over 1 plus x? I do think that we came up with one. Where is it? It's not that one. It is this one. All right, so here it was. It was this guy that's right here. I'm just going to steal it. Steal you away. Copy. All right, let's go back to where we were. Wow, we've covered a lot already. All right, I think this is about it. All right, so let's paste this guy right here. And now what I want to do is just stick this thing in here where there's an x. It doesn't affect the little alternator here because there's no little x to plug it into. So summation n equals 0 to infinity, negative 1 to the nth, and then in the place of x, I'll put x squared and then raise that to the second power. Power to a power, I multiply the exponents, and then I get to the 2n power, which is exactly what we got right there. All right, so indeed, it seems to work. Okay.